Great. Okay, recording again. So welcome back to the first lecture now in the arithmetic harmonic analysis course. We'll actually dive into doing the circle method now in terms of Waring's problem. Okay. So in particular, I'll be breaking down how to do sums of 5 or more squares. All right. And well, there's a little outline, but let's just go ahead and sort of jump into it. So to remind you, the Hardy-Littlewood theorem, and also to write it a bit differently. What we want to know is we want to know how to write each natural number as a sum of a certain number of kth powers, where I fix my degree k. Okay. And what I need to do is I need to also fix the number of such powers, which will be denoted by d. I'm actually going to take a different perspective rather than just thinking about this as the sum of d kth powers. I'm going to think about this as the number of points, number of integer points on the hypersurface, on the real hypersurface defined by this. Okay. And now the Hardy-Littlewood theorem says that when my dimension is big enough in terms of the degree, so it turns out to be something exponential in degree, then you actually can write this representation number as some factor that depends on n, and I'll get back to what that means in a moment, times a d minus 1 dimensional volume of this hypersurface, of the real hypersurface. This d minus 1 dimensional volume grows like this. Okay, and before we saw that factor ck of d, it doesn't depend on n at all. It's some gamma factors that I forget off the top of my head. Okay, but the important thing is that this is a real volume on a real hypersurface. Okay, and now the second part is that this other factor, that's a math frac s, standing for singular series. It turns out that this actually depends on n, which is something I didn't make clear in the introduction, but it fluctuates depending on n. However, when you have enough dimensions or enough variables, it does so in a controlled manner, meaning I can find some positive finite constants such that it's always sandwiched between these. For instance, if you have a sum of 5 or more squares, then the singular series, which also depends on dimension and degree, actually is always between, say, 1 over 100 and 100. Okay. But it does fluctuate, and that fluctuation is taking into account various p-adic effects that are happening, or biases that come into play. And this is all up to some lower order error term. Okay, and that error term compared with this is of smaller size. Great. So we're going to do this again for degree 2 and degree d. Just going to throw up a slide that has a bunch of notation on it to cover my bases. But you know, if at any point you've forgotten what it is, just remind me to remind you. But I'll try and go over it as I actually use it. Okay. Two big points to take away are the way I've defined my character, E of t. I use this to define my Fourier transform in a certain way. And that means various factors, when you say differentiate, are going to be are going to be minus 2 pi I, and so on. Another takeaway is how I'm going to be talking about how I'm going to compare orders of magnitude. And I'm going to use this notation, which the first part of it I learned from notes and papers of Tau. And the second part of it is really just the natural follow-on from the previous two, and is not used to mean asymptotically. Okay, but we'll get into that. Well, I mean, we'll start using this stuff, and as we use it, you know, it'll become more second nature. It's just notation. All right, great. So sums of 5 or more squares. Again, the dimension is going to be d. Now I fixed my degree to be 2. Okay, so k is now always 2 and fixed. Right. I'm going to write the arithmetic sphere of radius root n as the number of as the integer points, not the number, but as just the integer points, the collection of integer points, so that the sum of the norm squared is n. Okay, so This is a subset of the real sphere of radius square root of n. All right, and I'll use R of n to denote the arithmetic volume, which is just the cardinality of the set. We want to prove the following asymptotic statement, which says that the volume grows like some singular series times, oh, there's a constant in here that I missed, C, D, some gamma factors times n to the d minus d over 2 minus 1. Okay. Now, if we write R as the square root of n, then what we see is for the sphere of radius R, we have a factor growing like R to the d minus 2. And again, there should be some constant here, depending on the dimension, some gamma factors here, depending on the dimension. Okay. This, if you're paying attention, you notice this is a lot smaller than the usual d minus 1 dimensional volume on a real sphere. Right. So normally you expect that constant is going to be, sorry, the real volume of your sphere on radius R grows like R to the d minus 1, not R to the d minus 2. Okay. But in this case, it's actually appreciably smaller, right, for large R. But this is the right thing. And this is, to answer Chuang's question from the introduction, this is the reason why there's a difference in the ranges of the continuous spherical maximal function and the discrete spherical maximal function. We'll see precisely what I mean by that later on. Not in this lecture or the next one, but once we get to the spherical maximal functions. Okay. This constant right here is actually the same one that arises in the continuous case. Sorry, in the discrete case right here, where I look at the C2 of D that I'm alluding to above. Right. But there's a heuristic that tells you R to the d minus 2 is actually the right amount of volume to expect. Okay, so let's go over the circle method heuristic, which is very important. So I'm looking at the number of integer points such that x squared equals n, right? Now, so okay, I can rewrite this actually as all the x that are integers, but because the sum of squares is positive, each value is actually lying in the range of minus square root of n to square root of n. Okay, and again, I need that the square of x, square of the norm is equal to n. Well, most of the integers, so if I assume that there's some sort of, if I don't expect there to be any bias, right? Like if I can represent n in a certain number of ways, then I expect that I can represent n plus 1 in roughly the same number of ways, and n plus 2 in roughly the same number of ways, and so on. Then when you expect that to be roughly to be equidistributed, what you predict is that, okay, I have most of my integers in this, right? So most, let's say xi in this interval minus root n to root n are of size root n. So meaning up to some constant. So for instance, 99% have size greater than or equal to root n over 100. Okay. So most of my integer points here are going to have very large coordinates, right? They can't be much smaller than the power of the square root 10. Fantastic. And I'm expecting them to be roughly distributed. So the number of points, so if I take all my n, if I consider n plus 1 up to 2n, and I expect it to be roughly the same number of points on each of these, then what do I have? I have the length of this interval, which is something of size root n, and each coordinate, that's d coordinates, so it grows like that, but it's uniformly distributed over the absolute value of x squared, uniformly distributed over this range, would suggest that only 1 over n possibilities for each element of this range, each representing each number n plus 1 and so on. Okay, and when you do that, this is actually just n to the d over 2 minus 1, right? This probabilistic argument. So this is really assuming that there's no bias between n plus 1, n plus 2, and so on. Okay, but it turns out there are actual biases, and this isn't. This is just a heuristic. It's not at all a proof. I gave myself an extra page in case I needed to write more. Were there any questions on that heuristic?
So like, this would change if you had a different power than 2, right?
Absolutely, absolutely. So if I had degree k, say, then this becomes a kth power here, right?
Yeah.
And here as well. And so then this became that, and you get n to the d over k minus 1, which is exactly the order of growth appearing in the Hardy-Littlewood theorem. Yeah. And more generally, if you have like a homogeneous form of a certain degree, of a degree k, you'd expect the same sort of growth. Right. Okay. So again, there are some caveats to this. Right, the heuristic, it's only going to work whenever whenever this is positive, right? So if I have n to the d over 2 minus 1 actually growing as a function of n, that means, of course, that d over 2 minus 1 has to be positive, or in other words, d has to be greater than 2. So this only has a hope of being true in 3 or more dimensions, and we're actually going to only prove that is true in 5 or more dimensions. Sorry. And it turns out that these biases I alluded to actually do appear in smaller dimensions, in 3 and 4. So in 4 dimensions, in particular, that singular series that I talked about, but I haven't given much information so far. This thing right here fluctuates a lot. It can go to 0 along some subsequence of R, and it can go to infinity along another subsequence of R. In particular, this is not true right here when we have 4 dimensions or 3 dimensions. Okay. But before we get started, let's actually show that that we do expect that this upper bound we predicted by the heuristic is almost true. We're going to prove an asymptotic. That takes a bit of work. So to kind of reward ourselves along the way, let's prove that we can get an upper bound that's almost the right shape. So this notation here is going to mean that, so if I have f of x is less than to g of x, that means there exists some constant positive such that f of x is always less than or equal to c times g of x in absolute value. If I add an epsilon here, and I have some parameter like x to the epsilon, then I'm saying there exists some c, depending on epsilon, x to the epsilon. Okay. And so this is saying that for any power bigger than d over 2 minus 1, the number of points on your sphere is controlled by the n to that power. Okay. And this will actually work in 4 or more dimensions. So when I said that there is some bias that occurs in 4 dimensions and that bounds for the singular series aren't controlled, they can go to 0 or infinity. They can only do so in a subpolynomial rate. Okay, it can only grow like n to the epsilon for arbitrarily small epsilon. Okay, great. Oh, right, proof of the proposition. So this is I don't know, I like this proof. It's cute, in my opinion. So we'll write so if we are looking at the number of ways to represent this as x1 squared plus up to xd squared. Well, we write this as n minus x1, or let's say, yeah, x1 squared minus x2 squared. And that equals x3 squared plus up to xd squared, right? D is greater than or equal to 4. Okay. Now, just to remind ourselves, we also had that the xi, each xi, has absolute value less than or equal to the square root of n. Okay. Now, what I'm going to do is I'm going to let each of these, oh no, I'm sorry, I did it the wrong way. I need to erase wrong partitioning. Great, yes. So we'll write this as n minus x3 squared minus dot 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 minus xd squared equals x1 squared plus x2 squared. Sorry, right, where each xi is bounded between is at an absolute value at most the square root of n. Okay, so the important factor we're going to use here is that in z adjoin I can write this as a product of two things. So in I is, of course, the square root of -1. So that equals x1 plus I x2 times x1 minus I x2, right? As Gaussian integers. The z adjoin I is the ring of Gaussian integers. Now, an important fact here is that if x1 squared plus x2 squared is equal to some m, then, sorry, I should say it this way. The number of x1, x2, and z2 such that x1 squared plus x2 squared equals m is very small. Okay. In particular, this is less than or equal to some e to a constant log m over a log m. This being the divisor bound. So why is this true? Well, I've taken my integer m and I've written it as a product of two things, okay? Say a Gaussian integer z1 times a Gaussian integer z2. And the claim is that there are at most m to the epsilon ways to write this any integer as a product of two Gaussian integers. The reason that's true is because Gaussian integers are a unique factorization domain. In fact, they're a Euclidean domain. And so this divisor type bound applies. Okay, the details are in Hardy and Wright. And I'm going to take that sort of elementary number theory fact for granted instead of getting into like algebraic number theory and and estimating powers of 2. But once I know any given z1 and z2, it turns out that z1 plus z2 is twice x1, whereas z1 minus z2 is there's 2 times I of x2. And so knowing the pair z1, z2 is in a bijection with the pair x1, x2. Okay, so that means they're most m to the epsilon, x1 and x2. Now, how do I apply this to the red? Well, I let the xi's be arbitrary when let's x3 through xd be arbitrary. In their confined intervals, right? In minus root n to root n. And so there are at most n to the d over 2 minus 1 such possibilities times, well, whatever this number is to the epsilon. But this number is always smaller than n, so it's always smaller than n to the epsilon. Okay, and that's the proof. Is everyone happy with that? I will take silence as an affirmation. So that was cool. That quickly gave us a bound of almost the right shape and size for the number of ways to represent any integer as a sum of, oh wait, actually that applies for all d greater than or equal to 3, doesn't it? Yes, it does. Okay. Sorry, so this gave us a very swift proof, just using something about Gaussian integers, showing that the volume of this arithmetic sphere is bounded by what we expect it to be from above. Okay, or almost that at least. So now, moving beyond this divisor bound and actually making this into an honest asymptotic, an upper bound was no easy feat. It was certainly a groundbreaking work. And when Hardy and Littlewood did this, and in fact, we're able to give asymptotics. It's certainly one of the most beautiful paradigms in analytic number theory in all of mathematics. So what was their starting point? Well, how did Hardy and Littlewood do this? They started by thinking of the delta function as in terms of the residue theorem from complex analysis. So I gave a different representation in the introduction, and we'll come back to that in a minute. But there's another way to write the delta function. So it turns out that the delta function at -1 can be written in terms of the residue theorem, right? So the residue theorem tells us when you can pick out, it tells you how to pick out the residue of a meromorphic function, right? And you only have a residue if you have a 1 over z type term, or 1 over z minus, say, a, and you got a residue at a. And it's just the way of writing this is if I take a circle, say the unit circle in C, and I orient it counterclockwise, then this integral, this complex analytic integral, is equal to 1 when k is -1, and it's 0 otherwise for any other integral k. Of course, this doesn't make sense. The integrand doesn't make sense for non-integral k, for arbitrary non-integral k at least. And you might think that, oh, well, okay, I had delta of 0 before. Yes, the reason why this is shifted off by 1 is that the dz here is hiding a factor of e to the I theta. Or if I normalize things correctly, then it would be 2 pi I theta. But that is taken care of by this normalization right here. Okay, so that's something from undergraduate courses, and presumably everyone did calculations involving the residue theorem. I'm not going to go into that much more other than to allude how Hardy and Littlewood did this. But they use this sort of residue theorem here. Instead, we're going to take the modern viewpoint, which I believe was introduced by Vinogradov. And it's again, this oscillatory integral representation we saw in the introduction. And you can see that this is, it's very easy to verify this claim, right? So delta function, delta at n, just to remind ourselves, is 1 if n is equal to 0, and is 0 if n is not equal to 0. Implicitly, I'm forgetting to write a 0, a delta sub 0, to indicate the point at which it's 1. But when I don't write such a point, then I'm just saying this delta at 0. Great. So when n is equal to 0, this integrand right here is, of course, 0. And so then e to the 2 pi I 0 is just 1. The integral from 0 to 1 is just 1. And it's 1 as I claim. Now, when n is non-zero, then you have oscillations coming into play, right? Oops. And you have full periods that arise. So, right, so I get a full period of the real and this, the real and the imaginary parts. And they cancel out each other perfectly for any non-integral n, for any non-zero n. That's integral. So how do we exploit this? Well, we're going to take our exponential sum, and just formally working for the moment, let me write this as, I take the infinite sum, either 2 pi I n squared t, or minus 2 pi I n squared t. And I look at that at the dth power. What that does is this product turns into a sum inside the exponentials. And so that I get, the sum of n I squared. And if I'm able to collect all of those powers, again, not really thinking about this as an honest function, there's just some counting as a generating function, then you find that you get this way to represent, you get this series whose terms are the representation, the number of ways to represent n, okay? And then formally, you just apply this oscillatory integral version of delta above to pick out r of n from that exponential sum. All right, that's all formal. There are a lot of issues when it comes to trying to make this finite or discussing convergence. And a very elegant way to get around that is just to smooth your exponential sum. So we do that by picking some Schwartz function, right? So Schwartz just means that I can infinitely differentiate it, and it has polynomial decay of all orders as you go to infinity, as do all of its derivatives. Okay, so it's very rapidly decaying, and every derivative is very rapidly decaying. We're going to actually choose a Schwartz function that's identically 1 from minus 1 to 1, and is supported in minus 2 to 2. So it's compactly supported. Now that was one-dimensional, and we need a d-dimensional version of it. That d-dimensional version is just done by making it a tensor product. So each coordinate, I have phi, I have this original Schwartz function. Okay. And then we'll also need to consider dilates of it, where I've dilated each coordinate by r. So when you do that, you can reform this exponential sum above that didn't quite make sense. Simply, just as given in this first display equation. But the penalty you're paying here is that you don't get the original representation function. The representation function itself is also smoothed out. Okay, it's also compactly supported. And therefore this sum overall is finite, which is great for us because any trigonometric polynomial is also smooth, right? But what really makes this work is that as soon as I pick this r to be bigger than the square root of n, so that each of the coordinates can be up to size square root of n, an absolute value, then I know that r prime of n is equal to the original representation function at n. It's not for bigger values of n, but it is at that n. And so we'll always have this assumption here. We're always going to have r greater than or equal to square root of n. Actually, at the end, we'll take r equal to the square root of n, or the ceiling of it. It's probably better for writing sums and such, but it's a minor point. And therefore, when we write out this thing, right? Turns out that we can apply our delta function and just get this. Okay, so this smoothing actually makes things rigorous. Actually gives us a rigorous way to look at this infinite exponential sum. Often in a lot of these treatments, say in Davenport or Vaughan, they're going to make this a sharp cutoff. And I don't want to do that because it just makes the analysis you're doing more complicated. And you have to use more special functions and so on. Yeah. So again, just the smoothing it's going to be an important technical tool for us. It's something that's done a lot more in harmonic analysis rather than analytic number theory, but I think it's catching on more in analytic number theory. In particular, right, I'm using this function phi, which is Schwartz, because the phi naught is Schwartz and the product of Schwartz functions is also Schwartz. And so we're golden in that regard. Yeah. Oh, I have a chat. I'll come back to that in a minute, or at the end. Okay, so where were we? So I have these finite exponential sums. Technically, I've actually smoothed them. I had a sum phi of n over r. This for some large r. This is all n and z. I should be saying r. But ignoring the smoothing factor for a moment, let's just figure out, let's get a little acquainted with this exponential sum. The first thing you can easily compute is when t is equal to 0, right? Again, when t equals 0, each of these is 0. And so this whole thing is 1. And I'm really just counting all the number of points up to size r. Okay, that's a lot. That's the size, this is of size r, of course. That's really big. And if we are plugging that into this sort of thing, where you look at the d-fold product of it and do a trivial bound here, we're only getting r to the d of size, which is much bigger, which is square root of n. So n to the d over 2, that's much bigger than n to the d over 2 minus 1. So the reason why this isn't a big issue is because there's actually a lot of cancellation at other values of t, right? So near 0, the sum will stay roughly of size r because a trigonometric polynomial is smooth. So by continuity, if I'm r at one point in a small enough neighborhood, I'll be at least r over 2. But if I move sufficiently far away, and in this case, say I take t equal to be 1/2, then that sum is actually always small. This sum is always 1 or minus 1, which is vastly smaller than r. And that's because, and that depends on whether or not r is even or odd. Okay, and in particular, why does this happen? Well, when I take n to be, when I plug in little n here as a 0, as an even number, times 1/2, I get squared, and I end up getting something that makes this exponential 1. However, when n is odd and I square it, it's odd again. Times 1/2 here makes the exponential minus 1. So I'm alternating, adding 1, minus 1, 1, minus 1, and so on. And therefore, I can only ever be at big size 1 or minus 1 in absolute value. Right? So there's a huge amount of cancellation at this other precise point. And it turns out that you can make this rather precise, and any other non-integral but rational point, there's significant cancellation in the sum. And again, because of the smoothness, there's a lot of cancellation near each of those rational points. So there's a couple of pictures on how to make that, how that looks, right? You see here at the point 1/2, it's basically 0. It's turning out it's just 1 or minus 1, right? again, oh, sorry. So what is this? This right here is going to be the sum of e n squared t, where this is t. And this is n equals 1 to 10,000. Yes. Okay. So that's what this function is over here. And the points I sample that are of roughly size 1/100 apart as you go along. Okay. So again, at t equals 0, you see this big peak. That's of size 10,000. At 1/2, I see 0. And then at some smaller things, something like 2/5, 4/5, 1/5, I get some cancellation. It's not quite 1,000, but it's pretty close. And at some other rational points, I think this is a 1/6, perhaps. And if you look at a third, you should get something too. A third somewhere around here. You see that you're starting to get some peaks, right? And of course, in a small enough neighborhood around this, this exponential sum is still pretty high. Zooming in further, so taking Q to be, so the spacing was 1/100 here, whereas the length of the exponential sum was 10,000, so square root the spacing. If you zoom in and you try and look at each 1/10,000 points, you see a lot of jumping happening around here. Okay, but you still see the same sort of qualitative phenomena, big peaks at rationals of small height for this exponential sum. Great, so there's a lot of cancellation in our exponential sums. You need to understand that in terms of the oscillation, in terms of the oscillatory interval representation. So with this in mind, I can sort of give an overall sketch of the proof. Right. So we use our oscillatory integral formulation of the delta function to examine the behavior of the exponential sum at each of these rational points. And the way we're going to do that is by using Poisson summation. Poisson summation is a very good way to transform an exponential sum into a dual exponential sum and to pick out the big components in the dual. Now, the way this happens, the big component turns out to be the 0th frequency. So for each of my rational points A over Q, where A is co-prime to Q, so it's a reduced form, this Poisson summation gives you a lattice of frequencies that depend on Q. There are multiples of 1/Q, integral multiples of 1/Q. And the 0th frequency turns out to be the biggest one. By far, it dominates the rest. For us, that means we'll discard all n/Q where n is non-zero. Doing this is pretty good when Q is small, because the differences in size from n/Q and m/Q, when n and m are not equal, is pretty large. It's at least size 1/Q. And when Q is small, that's big, right? If Q is equal to 1, that means it's the next integer. Or if it's 1/2, it's only half away. However, when Q is quite large, there's not a lot of cancellation there. There's not a big gap there. And you're really piling up on top of each other. You're not giving yourself enough room to cancel. To overcome this, this is where Hardy and Littlewood introduced their paradigm of major and minor arcs. On the major arcs, you're able to run through this Poisson summation argument and put the non-zero frequencies into our first error term. The minor arcs, we're going to treat differently. We treat them by using Weil's inequality, which is something that Hardy and Littlewood knew. It was proved, 5 to 10 years before their circle method result. This basically says that when Q is large, you have a lot of randomness in the exponential sum in a quantitative way, and you get a hold of that without doing Poisson summation. You do a different process entirely. And the minor arcs will be handled by that. That'll be our second error term. Okay. We're going to have to optimize, of course, the where we choose our major arcs and minor arcs. So the rest of the argument proceeds by processing the major arcs. we want to extend the oscillatory integral that arises in doing Poisson summation to the singular integral. And we'll do this by making use of stationary phase, the principle of stationary phase. Then we extend the singular series, again, using a principle of stationary phase, but on Z mod Q. And after that, the final two pieces are to show that the singular integral grows like we expected it to. It's the volume of this real volume. And the singular series is actually a product. So we have to convert a series into a product and interpret each one of those factors as a p-adic singular integral. We're going to get started on the first parts of this proof, probably covering 1, 2, and maybe 3 by the end of today, maybe even 4, who knows, we'll see. And certainly have to proceed with the others next time. Great, so are there any questions on what the problem is that we're trying to do or anything at this stage before we get into actually proving it? Gave myself a couple more slides to write anything. Someone had a question? How about Rob? I think you made a comment in the chat. Would you like to say what that is right now?
Yeah, so this isn't important. I just sort of left it there in case anyone was interested. But the divisor bound you used for the Gaussian integers, there's actually a version of it for arbitrary number fields. And so sort of the obstruction to like an obvious divisor bound for arbitrary number fields is that arbitrary number fields might have infinitely many units. But you can get around that problem by sort of restricting the coefficients to lie in a certain interval, which naturally arose in the problem you were considering because x1 and x2 were bounded above by root n.
Great point. Thank you. Yeah, I think one of the things Rob is saying is when you think about these in terms of ideals, you have the divisor bound. And then to pass from ideals to actual numbers, you can restrict the coefficients.
Yes.
Cool. Cool. All right, I will go on with the getting into the proof. Let's see how far we can get today. The first piece of what we're going to do is we have an integral from 0 to 1 of e minus nt times some exponential sum I was calling h sub r of t, right, with respect to dt. We're going to, this interval 0, 1, I'm actually identifying with the torus r mod z by this character e to the 2 pi I t. So what this means is if I take any interval inside of R, I'm going to look at that interval mod 1. And in terms of this interval right here, where I'm integrating from 0 to 1, I'm looking at that representative in the interval from 0 to 1. And that, so if my interval were say to be, it was a straddle 1, as a little interval around 1, then it actually breaks up into 2 intervals. One that's the left half before 1 and the right half following 0. But I'm going to still refer to that as an interval or an arc. Yeah. The nomenclature here that I've started to use is the major arcs and the minor arcs. We think about, we use the term arcs because Hardy and Littlewood use the residue theorem. And they're actually integrating over an honest circle inside the complex plane. We have the same thing here, but we're thinking about R mod Z as that circle, as the torus as that circle. And an interval projected, an interval from R projected onto R mod Z as being an arc on that circle. Okay, but it's normalized so the circle has length 1 rather than 2 pi. Now there's this thing called the Fourier dissection, which it happens at all levels, and it is used to break up the interval 0, 1 or the torus R mod Z into a partition of arcs. this partition means that no two separate arcs overlap, except maybe at the endpoints. Okay, that's great. So what does all that mean? Well, what's the Fourier sequence? Up to some level x, which is just some natural number, say, could be a real number if you wanted it in this definition. It's going to be all of the rational points in a reduced form, so a over q, where a and q are coprime, such that the height of that rational point, which is the denominator q, is at most size x. Okay, it's smaller than x in particular. I chose less than instead of less than or equal to. But you could make it less than or equal to if you wanted. You define your arcs as the projection modulo 1 of these intervals. So I take that Fourier sequence. Sorry, I just gave you a set. I didn't tell you how to make a sequence yet. So the set is all of those rational points. The sequence is order the rational points in terms of the real absolute value. So one of the points that you can take would be, that I haven't really mentioned in here, but it should have been accounted for, is also the point 0 over 1. This is the leftmost point. This is equal to 0, and it would be the first element. Once you have this sequence, you can actually take an interval to each element of the sequence by forming these quotients. And it looks weird, and it actually is quite weird. These things relate to continued fraction extensions and so on. I'm just going to take for granted that these intervals partition the torus for any x, right? Any x, I get a partition of the torus. As x increases, I get more rational points, and these arcs get smaller. I'm going to take that for granted. That is a nice elementary exercise in number theory that you can also find in Hardy and Wright. And I'm also going to take for granted additional exercise that each of those arcs has length about 1 over q times x, where q is that denominator, and x was the height or level of the Fourier dissection. So this, I'm just using this to cut up the torus, and so that I know I have this length roughly for each of these arcs. The precise endpoints won't really matter much for us. And when I say has length essentially this size, I mean ei bar of a over q is say less than or equal to 20 over qx and greater than or equal to 1 over 20 qx. I think you can actually make those 2s instead of 20s, but just to be safe, let's take them to these 20s. Once we do that, we've broken up our torus into a bunch of pieces, right? So I have my torus, I say 0, 1, and I've got a nice arc here. I've got maybe an arc here, and another arc here, a fat arc around here, around 1/2, and so on. Once I've partitioned my torus, I use that to partition my integral by just restricting the integrals of those intervals and summing over all the possible intervals. Since they partition, I get everything. So some more notation that came into play in this case is I need a way to write all of the reduced fractions mod q. I'm just going to write that as u of q, u being for units mod q. Should be easy to remember. From here, we're actually going to translate those intervals I over q so that they're roughly symmetric around the origin. You can see these endpoints are slightly different from A1 and A2 and Q1 and Q2, but that's not going to be, that's not really mattering for us because of the 1 over QX for the length. Once we do that, of course, that means by changes of variables, we get something of the following shape. So this HR of t was that exponential sum again, just sum of e n squared t. for vectors, smoothed out, sorry. And when you make the change of variables, what you end up getting is this space that comes out from before times these intervals, where the I of A over Q's are, again, they contain the origin. They're almost symmetric about the origin. And I got this as a sum over all the points in the Fourier sequence. So the first step, and after we get to this, we'll end for today. The first step is that by having made that translation, we're actually in a very good place to apply Poisson summation. Okay. So how are we going to do that? We're going to write out our HR of T as a sum over some Schwartz function over a lattice, sample that lattice points. This is exactly what the Poisson summation is set up to do. Now, when you do that, so Poisson summation says that when I sample over a dual lattice, the Fourier transform of this thing, the real Fourier transform of this thing, I get that it's equal to the original thing. Now, the thing that intervenes here is this shift A over Q. We want to exploit that as A over Q. We know that when I take T to be 0, so that I'm looking at the rational point at H of A over Q, HR of A over Q, right? I know this can have a lot of cancellation depending on Q, or a lot of constructive interference too. And this actually gets reflected in doing the actual Poisson summation. And you find out you end up getting these sorts of exponential sums, where my dual lattice is now depending on Q. These exponential sums are Gauss sums. Okay, they're actually normalized for us because the normalization just comes out and it's easier to keep track of. What do I mean by this? So I'm looking at B mod Q. This B is a vector, so it's B in Z mod Q to the D. And when I write this, I actually mean sum of BI squared. I'm just being a bit lazy and I'm taking the norm everywhere squared, but norm doesn't make sense mod Q. So I mean just the algebraic definition of it, okay? And of course, the dot product is also going to be defined algebraically. For two vectors, it's just the sum of BI and MI for I equals 1 to D. It's easy to see because each of these, so the sum of BI squared minus BI times MI, since these sums are over each coordinate, you can split up this character into a product of D characters, one for each coordinate, and therefore this sum as a product of one-dimensional Gauss sums. Now the trivial bound for Gauss sums is just I apply the absolute value. Okay, so this is less than or equal to that by the triangle inequality, which is all ones. Z mod Q has Q points, so the Q to the minus D here just balances out the Q to the D here. And we always get a bound of 1. That's a very trivial bound. There will be more cancellation that we'll find later on. Once we have this, it turns out that we just rewrite our previous expression as a sum of Gauss sums times some continuous factors. And of course, we're integrating over each of the arcs. I did not recall Poisson summation. All right, so I will stop there today. And then I'll pick up with how to get this identity next time. Are there any questions before I stop the video? All right, I will stop it.